And actually 5.2 is doing a couple of things that are related to what we were just doing with the Riemann sums. We're thinking about area here, but we're just going to introduce the idea of a definite integral. And a definite integral relates to the net area under a curve. So let's just take a look at the Riemann sum here, noticing that if I were to compute the Riemann sum here, all of these rectangles are below the x-axis, right? And therefore, each of these function values that we get are going to be negative, right? So for instance, here, 1 minus x squared, if I compute f of 1.25 here, or f of x is 1 minus x squared. So if I do 1 minus 1.25 squared, I get a negative value, negative 0.5625. And same here, if I do 1 minus 1.75 squared, I get another negative value. F of 1.75 is negative 2.0625. And so on, like all these values here, again, would be negative values. So because these are below the x-axis, they have negative function values. So the Riemann sum here actually gives me a negative area. So it computes the area of the region below the x-axis of the rectangles, actually, I should say, below the x-axis as negative areas. Right? We typically think of area as a geometric quantity that's always positive. So we're going to adjust that notion a little bit here and think of, we're going to think of the net area as corresponding to the net area being where we consider areas that are above the x-axis as positive areas, areas below the x-axis contribute a negative area. So area above x-axis is positive, and the area below contributes a negative quantity. So those two things combined together give us the net area. So some regions might lie above, some regions might lie below. And we see that when we compute the Riemann sums, the rectangles that are above the x-axis contribute a positive value, and the rectangles that fall below the x-axis contribute a negative value. So with that in mind, we can think of here our with that in mind, we can think of our Riemann sum here as we've got some rectangles that lie above the x-axis. Over here, we have some rectangles that lie below the x-axis. So these rectangles here contribute positive value to the net area, whereas these ones are below the x-axis. These contribute a negative value to the net area. Okay, and so we see that it looks like here that the sum of the areas above the x-axis would contribute this small positive value here, and then the sum of the rectangles below the x-axis here are a larger contribution. They're somewhat larger area there that lies below. Hence our net area is going to be a negative value there. Okay. So here we've got the regions above and the regions below will combine together to form the net area, or in this case, the Riemann sum that represents an approximate net area. Okay, so just kind of splitting, notice that we actually split the areas between the regions above and the regions below. But let's think about it more generally here. It says the Riemann sum here, which we know is just the sum of all the f of x k star delta x, approximates the negative of the area of the region that's below the x-axis on this curve. Since all of these function values here are negative, for all these rectangles, it's like now the height of the rectangle is considered a negative value. Okay, so the sum of f of x k star times delta x is negative. So that gives us this negative Riemann sum. And therefore, if we consider this an approximation of the area below the x-axis, then what we're really considering here is that the area of the region below the x-axis is thought of as a negative area, a negative region. So the net area, which we'll define here, is the area where we consider the regions above the x-axis as positive areas. So these regions that lie above the x-axis will contribute a positive area to the net area. And then we'll subtract the area of the regions that lie below the x-axis, and that'll contribute a negative area to the net area. Okay. So the net area of R is the sum of the areas of the parts of R that lie above the x-axis minus the sum of the areas of the parts of R that lie below the x-axis. Okay, so let's just practice this idea a little bit. Okay, yeah, actually here we're going to define the definite integral first. It says the Riemann sums for f on AB give approximations to the net area of the region bounded by the graph of f and the x-axis between x equals a and x equals b, where a is less than b. So how do we find the exact net area? So the exact net area, well, we know that computing our Riemann sum, remember this is an approximate area. So if we want to make it an exact area, we take the limit as the number of rectangles approaches infinity. Okay, so So by doing this, now we're essentially filling in all the little gaps that are left when we use rectangles to approximate the area. So what's happening here is the rectangles themselves are getting infinitesimally thin, and therefore they're filling in all the little gaps that are left when the rectangles themselves don't quite fill in the area perfectly. So this will give us the net area under the curve, which here we'll actually define as the integral from a to b of f of x dx. Okay, so we've seen this notation with indefinite integrals. So the idea is now putting these things here. These are called the limits of integration. A to b. These now represent the net area under the curve. Okay, so here's a picture to kind of see how that basic idea works. We've got the Riemann sum here with 6 rectangles is not a perfect estimate of the net area, since of course we see there are large gaps between the rectangles and the curve. So we increase the number of subintervals here. Let's do 40 subintervals with 40 rectangles. And what we observe, it does a better job of filling in the area. So this is more exact, but not perfect, because we still see there are little tiny gaps between the curve and the rectangles, approximating rectangles. So we'll increase it to 75 here, and we see that, okay, that does a little better job and fills in the gaps a little better, but it's still not perfect. You still have little tiny pieces hanging over the edge and little gaps underneath. So in order for it to be the exact area, we need to take the limit as n goes to infinity to get the exact area. So essentially what happens is that it makes these rectangles very, very narrow. So their width is going to 0, right? So as n goes to infinity, as the number of rectangles approaches infinity, notice that delta x, the width of each rectangle, goes to 0. So it kind of fills in the area perfectly with no gaps and no little pieces hanging over the edge, right? So all the rectangles here, as we take them to infinity, fill in the area under the curve perfectly. So here's a very technical definition, which is the general Riemann sum. This is not any different than our notion of a Riemann sum before, except for one thing, is now we're not assuming that delta x is the same on every subinterval. Here, delta x could be different. Okay, so here delta x sub k will be the width of the kth subinterval, which here in this case could be different widths. This is just a more technical variation of the Riemann sum that we had before. This one is general in the sense that it captures a lot more variety of the types of partitions that we can make on an interval. Okay, I'm not going to worry too much about this because this is not something we're going to actually compute ourselves, but it's more of a technical definition that allows us to then formally define what an integral is. Here, the Riemann sum, of course, looks exactly the same. The formula is the same. The only difference now is that these delta x's are going to be not necessarily the same for each yeah, rectangle. So here you could have rectangles with different widths. And so by defining the general partitions that way, we get this more technical definition of what a definite integral is. So we'll define the definite integral from a to b of f of x dx as here the limit as delta goes to 0. This is delta here represents our subinterval. I should say delta, oops, delta xk. So we know as n goes to infinity, delta x goes to 0. So this is kind of a generalization of that notion. So this could be the same as writing the limit as n goes to infinity. Okay, and again, the reason that they've chosen to adopt this notation is for technical reasons. But as far as we're concerned, if we want to compute a definite integral using this definition, we're actually not going to use a general partition, and we're not going to take the limit as delta goes to 0. We're going to take the limit as n goes to infinity. So this is, I think, perhaps a misleading definition as far as how we're actually going to go about computing these things. So kind of, take it for what it is, but don't worry about this too much. The important thing is to think about what this really represents here. This represents the exact area, or the exact net area under the curve f of x. Well, I shouldn't say actually, under the curve is a little misleading. So let me say between the exact net area between the curve and the x-axis. Okay, so this is the important notation that we're going to try and think about in this section. This more technical thing that we're describing here will be something we'll think about a little bit, but this is the important thing that we want to think about, is this net area. And I'm going to look at the notation here for a moment. We have the lower limit of integration, the upper limit of integration. We have the integrand here is the function that we're finding the area under. Dx is just our it's our differential, but it's more there to identify what integral what variable we're integrating with respect to. So this just kind of reminds us of the variable. But notice it doesn't really tell us much other than what variable we're integrating with respect to. It will play an important role when we're finding antiderivatives later on. So it's something that we always have to have there, but this is the function that we're finding the area under, and a to b would be the left and the right endpoints. So again, here to kind of think of the picture. You got some curve, maybe some parts of it are above the x-axis, some parts are below. So you got the region here that lies below the x-axis. You got some regions here that lie above the x-axis. Okay, So the integral from a to b of f of x dx is the net area. Oops, not the area, the net area of this region here, okay? So this function f of x, whatever it is, might have some parts that are above the x-axis. So the area under that region is a positive contribution to the net area. And then it might have some parts that are below the x-axis, which contribute something, a negative value to the net area. So notice here that if I, write the same function with respect to different variables, it's sort of reminding us here that the x here matches the dx here. If I use omega, then the omega here is the same, right? Or fs, this is ds here. So those variables match. So that's kind of what I'm saying when we write the dx here, it kind of reminds us what variable we're integrating with respect to. And here just kind of looking at a couple of things about the net area here. If f is continuous, and here actually let's be careful. It doesn't need to be continuous, but here continuity does guarantee that we can find the integral, because that means that the area is a value. You can always find the area if f is continuous, right? You can imagine if I've got some continuous curve, right? There's always going to be some net area that we can find underneath that curve. So continuous looks like this, but it actually doesn't necessarily need to be continuous, right? Because it says it could also just be bounded. As long as it's bounded on the interval with a finite number of discontinuities, then it's still you can still find the integral of it. So imagine you've got something that's maybe not necessarily continuous. It has a jump discontinuity somewhere. And actually that can happen at multiple points. But as long as it's finite, in other words, it doesn't have a vertical asymptote or something like that, you can still always find the net area. Like here, this region lies above the x-axis, so we can find the area of that region here. This region is below. So we can find the net area there, and here's, again, this part's above, so. And here, well, actually, I should be careful, like, okay. So yeah, even though there are these points of discontinuity, maybe here actually it's probably good to put a hole there. Oops. So even though there are these points of discontinuity, there's like a jump in the graph at those points, you can still compute the area under the curve, right? So this has a finite number of discontinuities. In either case, though, like if we imagine here from A to B, or from A to B, we can compute the net area under the curve. So these are conditions that guarantee that we have something that's integrable. Okay, so here's a picture that it can have a finite number of discontinuities. Like this has these 2 points of discontinuity, but we can still compute the area. So actually you would just compute the areas of regions 1 and 2 and 3. And so you would add the areas of regions 1 and 3 and then subtract the area of region 2. And that would be how you would compute the net area under this curve or in this integral. But let's think about the notation here. What integral does this Riemann sum represent on the interval 1 to 3? So I think this is just kind of reminding ourselves what the notation integral from a to b of f of x dx was written as the limit as delta goes to 0, sum from k equals 1 to n of f of xk star delta xk. So since they kind of tell us what integral it's on, or what interval it's on, we know the integral will go from 1 to 3. This is like our f of xk star here. So that means our f of x would really just be, okay, we'll replace xk star with x, and it's just 3x squared plus 2x plus 1. Okay. So really, all this Riemann sum here represents, or this, I should say this infinite, well, it's, okay, so it's a limit of Riemann sums is what it is, right? So what this represents is the area, the net area under the curve, 3x squared plus 2x plus 1 on the interval from 1 to 3. Okay, so, just I'm picturing it here. Maybe it's some parabola like this, I don't know exactly. But we know it's a parabola, so it's now representing the area under this curve between 1 and 3. But here, let's actually practice evaluating an integral geometrically. So at this point, we haven't really seen any other way of approaching this other than to think of this now as an area. So if I want to find the net area under the curve 2x plus 3 between 2 and 4, let's think about what kind of areas we're going to be computing here. So this is going to be the net area under the curve 2x plus 3 on the interval from 2 to 4. If I draw this out just to kind of help me visualize it, we can imagine, we know that this is a line, it's just a straight line. And what 2 points is it going to pass through at x equals 2? We can imagine that if I just plug in 2 here, you get 4 plus 3 is 7, right? So it passes through the point 2, 7 here. And then when x equals 4, 2 times 4 is 8 plus 3 is 11, right? So at x equals 4, it's 11. Okay. So whatever, the line itself would just be some straight line here. But we're computing of the area of the region that lies below it between 2 and 4. So our goal is to compute the area of this region here. Right? If we're trying to find the value of this integral, that's one way to interpret it. It's really just the area under the curve here. And so here's my f of x equals 2x plus 3. Notice that actually the region that we're trying to find here is really just a trapezoid. So we found the value at 2 and the value at 4, and those gave us, essentially that gave us the sides of our trapezoid here. This was 7 at this side, and this was 11 on this side. So to compute the integral here, well, one way to do it is to kind of just look at this as a trapezoid that we can find the area of. If you don't remember how to find the area of a trapezoid, well, you can just break it up. You got a rectangle on the bottom, and then you got a triangle on the top, right? So what are the dimensions of the rectangle here on the bottom?
It's going to be 2.
3 by 7.
2 by 7, right?
Yeah, excuse me, 2, thank you.
Because it's a width of 2 here along the base, right? Okay, yeah, it's scaled a little bit, so it kind of looks weird, but yeah, that's right. And so you got 2 along the base, 7 for the height. So the area inside that rectangle will be 14. What about the dimensions of my triangle here on the top? So again, it's going to have the same base, 2 on the base here.
And 4 on the height.
4 on the height.
Would be 4.
Yeah, 4 on the height here. Good, because it's gotta have the whole width, or the whole side there is 7, right? Or I'm sorry, is 11 for the whole height there.
We need to use the Pythagorean theorem for the horizontal line, or no?
Well, notice that actually we don't need the hypotenuse to find the area, right? We just
Yeah,
need base and
1
the
half
height.
base times height. Sorry, thank you.
So we actually, you could find it, but you don't really need it, right? So all you need is the base and the height here, and you get, yeah, so the area of this triangle here, 1/2, 2 times 4, which is I guess just 4, right? So the area of that piece there is 4. Okay, so putting them together, the area of the whole thing is 14 plus 4, so 18. Okay, so the area of that whole region here is 18. So that's going to be the value of this integral. It's 18. Okay, so we kind of broke this one down geometrically. So we see that, if we have lines, actually lines are pretty easy to find an area underneath, because it's always either trapezoids or triangles, rectangles. So you can always break them down into shapes that are relatively easy to find the area of. And let's look at a different example. Suppose I want to find the area under this line here. So you've got 2x minus 6 on the interval from 1 to 6. So again, this is a line, right? We can imagine here it's going to break down into, again, maybe some more trapezoids, but let's look at it now. Maybe it's a little bit different. So we're going from 1 to 6. And let's see, just to kind of get where the key points here are at x equals 1. Let's see, I get 2 times 1 minus 6 will be -4. So actually it's going to be below the x-axis there. So it starts starts at -4 here. And then at the right endpoint at 6, we get 2 times 6 is 12, minus 6 is 6. Okay, so it'll be up at 6 at the right endpoint. So we have this line here that goes through those points. Notice that at x equals 3, it's going to cross the x-axis. So that'll be another key point that we want to keep in mind. So actually notice here, this function f of x equals 6x or 2x minus 6 is partially above the x-axis and partially below the x-axis. So when we're computing the net area, we're going to compute the area of this triangle that lies above the x-axis. That'll contribute a positive value to the integral. And then we'll also compute the area of this triangle here, which will contribute a negative value to the net area. So we actually have two triangles that we're going to find the area of. So let's see. Again, let's break these down. The dimensions of let's look at the first rectangle here that lies below the x-axis. The point that we got here was the at 1 was 1, -4. So that means the height of this rectangle would be 4, right? So 4 along this side. And then the base along the other side here would be 2. Okay, so the area of this triangle here, and 1/2 base times height. So that would give me 4. So the area of that region that lies below the x-axis is 4. And then let's look at this other triangle over here. This one has the point up here at 6, 6, I believe, right? So the height here would be 6. And the base along this side would be 3. Okay, so therefore the area of this triangle here again 1/2 base times height. I think that's 9. So remember, now we're computing the net area. So we've got the area above the x-axis was 9 minus the area that's below the x-axis was 4. So we're subtracting that area, right? So the net area is 5. So it's finding the net area where we, right, this is the area. It's below the x-axis. So this one is subtracted from the net area. This is the area that's above the x-axis. So this is the one that's added or contributes a positive value to the net area. Okay, so actually part of this was figuring out, I kind of did this mentally, just observing that when I put x equals 3 in here, we get 0. So part of this was observing that it crosses here at the x-axis at the point 3, 0. So that was kind of a necessary component to figure out how these two triangles are formed. So with that in mind, let's look at something a little bit different. Notice that this one is not a line. Can you guys guess what kind of shape we have here?
It's like a sideways parabola.
It's not a parabola because it's got the square root on it.
I was saying it was like sideways, like it's like gradually increasing. No, sorry. Like,
Yeah, no, so it's not a, okay, I see what you mean. Yeah, so it's not a square root function either because it's got the square under here. Here's a hint. Let's just kind of look at it this way. If I were to kind of mess around with this equation a little bit, say I square both sides, and I get y squared equals 1 minus x minus 3 squared. And then I move this to that side. I just kind of manipulate it a little bit. Can you guys recognize this equation now?
a semicircle.
Good. It's a circle, right? So this is a circle with a radius of what?
Of 1.
Of 1. Good. And a center. What would be the center?
Would it be 3?
3, 0, right? So in fact, what we have here is something in this form, right? You can see it's in the form, just to remind you guys where I'm getting these values from. It's in the form x minus h squared plus y minus k squared equals r squared, right? So this is just the general formula for a circle centered at hk with radius r. So we in fact see that this is not the whole circle, but it's actually a semicircle. So the graph here is actually a semicircle. And the reason it's a semicircle is because when we take the square root here, we're only getting the positive values of y. So it's a semicircle. It's the part that's above the x-axis. Where it's here, it's centered at 3, 0. Centered at 3, 0. That's where the center is. And it's got a radius of 1. About 1 from either direction. So that's what the curve looks like, right? It's a semicircle centered at 3, 0 with a radius of 1. And let me actually blow it up here a little bit. Okay, so that's the graph of our curve. Notice that here the limits of integration go from 3 to 4. Okay, so basically we're finding just this portion of the circle. We're not actually finding the area under the whole circle, or not even the area under the whole semicircle, but just this right portion between 3 and 4. Can you guys remind me, if I want to find the area of this region, I'm going to take the area of the whole circle, and then what proportion am I going to take here?
Just a fourth.
Yeah, it's just 1/4 of the whole circle, right? So this is 1/4 of the area of the circle. So we can just do pi r squared and then divide by 4. And in this case, the radius is 1, so that makes it just pi times 1 squared over 4, which is just pi over 4. Okay, so this integral, without actually doing any integration, so to speak, we get the area of the region that this represents is pi over 4. Okay, so that one is a trickier one because here maybe it's less obvious what curve we're dealing with. But something to look out for when you got something in this form. This is a, okay, you guys can see this is a semicircle. You might even have some plus k out here if it's shifted elsewhere, but if you don't have that, this is just a semicircle. Okay, you guys have any questions about this one? No?
Whenever you have a function with a squared inside the radical, does that mean that you're always going to have a semicircle?
No. No, in this case, it's just something in the form like r squared minus x squared. This is a semicircle, for instance, if it looks like this.
Okay.
So this would be, if h is 0, if it's centered. So this would be one that's centered at 0, 0, right? But if it were r squared plus x squared, that would not be a semicircle. Or if it were x squared minus r squared, that would not be a semicircle. Those would be other shapes, maybe hyperbolas or things like that.
Oh, okay.
Let's look at something a little bit more conceptual here. Here the graph shows a function f with the areas and the regions bounded by its graph and the x-axis given. Let's just kind of break this region down. Suppose I want to find the integral from a to b. So that's from A to B here, right? They tell us here that that region is 12. And since it lies above the x-axis, it's just positive 12. What about the region from B to C? What would be the value of this integral? So from B to C, they tell us the area of this region is 10. But what's the value of the integral?
Would it be -10?
Good, it would be -10. Right, since that region lies below the x-axis. So it's a negative. And then let's take the area from A to C. Well, now we've got the region here from A to B that's above the x-axis, and then the region here from B to C that's below the x-axis. So going all the way from A to C, we're going to combine those two. So we have 12 is the area above minus 10, the area below. So the net area here would be 2. And then finally here, what about from B to D? So going from B to D.
It'd be 10.
So you would have 10 is the area below. So that would actually be a negative value it's contributing.
Okay.
And then C to D is above. So that's contributing a positive 8. Right, so you got the part here that's below contributes a -10 plus the part here above contributes a positive 8. So the net area would be -2. Okay, so I think the last couple things we'll look at before we have to end today will just be kind of identifying some basic properties. What they're showing you here is that the integral from B to A is the opposite in sign to the area from or the integral from A to B. So in other words here, if we switch the order of the limits of integration, so going from B to A instead of A to B just switches the sign. Okay, so in other words, if we go from right to left instead of left to right, then it's going to give us a negative net area or a negative integral. And then here, the integral from A to A, well, we can imagine here, from A to A represents the net area of a region with no width. So from A to A, of course, that's one single point, right? So the net area of a region with no width must be 0. So whatever the function is, doesn't matter. If I'm looking at just a single point there, the region that it represents is a region with just a single point. So it's got no width to it. Its width is 0. Okay, so those are a couple important properties. And then other important properties, the integral of a sum. So if I have the integral from a to b of a sum of two functions, f of x plus g of x, it's the sum of the integral from a to b of f of x plus the integral from a to b of g of x. This is sort of inherited from the same exact property that applies to sums. And of course, since we've defined the integral in terms of a sum, it inherits the property of sums that are very similar to that. And same with constant multiples. So in other words, if I take the constant c times f of x, integral from a to b, is just the constant c times the integral from a to b. So in other words, that constant multiple can be factored out from the integral. Again, that's the same property that it inherits from the same thing for sums, right? We know that it's just like factoring a constant out from each term of a sum. And then one other property allows us to split the region into separate integrals. Say I've got the integral from a to b, and then I've got some other point p. Then I can split that integral into the integral from a to p plus the integral from b to p, or sorry, from p to b. So it's like I'm just kind of arbitrarily picking a point here, whatever. Then it just splits that region into two separate pieces that we can find the area of each piece separately. So I think of it as kind of like slicing the region into multiple pieces.